Hello everyone. I'm sorry that I was not able to attend meeting in person. My name is Jinzhou Qi. You can just call me Tom. I'm a PhD student studying at the Duke University, advised by Professor Tingjun Chen. And today I'm going to present our work called the Programmable Millimeter Wave MIMO radios with a real-time baseband processing. So the content for this presentation is listed as the following. So first we have the background, and then for the contribution of this work, we're first going to introduce the Agora UHD system design, and then the integration with the 28 gigahertz phased array antenna module, which we're going to call palm bars in the future. And for the experimental evaluation, we first present the wireless quality of transmission, and then we present the baseband processing time analysis. So for the background, we've all been talking about 5G recently, and the advantage of 5G technology marks a great leap compared to the previous generations of the mobile networks. It's offering faster speed and also lower latencies. And the growth of 5G technology in recent years has been exponential. And according to this report, by the end of 2022, the 5G subscribers has already been reached to 1,000 millions. And this number is expected to be continuously growing, covering more than 40% of the world's population by the end of 2026. So with this growth and the expansion deployment of 5G, the demand for more flexible, scalable, and efficient network architecture has been brought up to the community. So this is what the traditional 5G baseband processing network architecture looks like. So we have the RU and DU, which is the radio unit and distributed unit, and it contains the radio frequency and also physical layers. So on the other side, which contains the MAC layers, the radio link control, the packet data convergence protocol, and the radio resource control, it belongs to the centralized unit, which we call CU. And conventionally, this CU is usually made of the specialized hardware. And because of this, this network infrastructure has increasingly unable to meet the dynamic and diverse needs for 5G services. And those rising challenges has led to the evolution and adoption of a virtualized radio access network, which is called vRAN. And the vRAN separates the network functions from the physical hardware and enabling them to run on the software on the commercial off-the-shelf servers. And taking the split option 8 as an example, is separating the physical layers with the radio frequencies. And there has been already some work investigating the this softwareization and virtualization with 5G FR1 massive MIMOs, such as the Agora, published in the Conex 2020. So, however, since Agora uses the special radio hardware, and which is the Iris board, so in order to provide, say, the access to real hardware platforms and the software supports for open source and the user-friendly massive MIMOs, it leads to our first contribution, which is the Agora UHD system design. So we first introduced the Agora UHD, which enables the UHD-based software-defined radios, which is the SDRs, to interface with the Agora. So which we can do experiments with the 5G Alpha 1 massive MIMO radios using more general USRPs. And let's just dive deeper into the our system design. So the this shows the Agora's design. So the Agora is a real-time open source software for massive MIMO baseband processing on the single many-core servers. So Agora supports two operation modes. So with the added flexibility to operate on DPTK mode. So this feature can be enabled for data streaming. So in the simulation mode, the Agora processes the emulated RU traffic generated by the host, where in the RU mode, which is the real radio unit mode, Agora processes IQ samples from the real radio hardware. The Agora supports the Iris radios hardware from the Skylark Wireless using the SOPI Iris drivers, and has been integrated with the sub-6 GHz massive MIMO platforms as part of the PAL Renew testbed. So similar to Algara, for the Algara HD takes a JSON format as input, which includes the configuration parameters of the physical layers, such as the signal bandwidth and the frame schedules. And it also takes the UHD parameters, which is the more radio, USRP radio hardware, such as the carrier frequencies and the RF channel and gains used for the program's initialization. So the Algara UHD for the Algara's UHD radio interface, the UHD radio is implemented using the native UHD USRP, the TXRX streamers classes object, which provides the functionalities to initialize, tune the radio hardware, to activate the TXRX streamers, and to stream the IQ samples between the host and the USRPs. So compared to the vanilla Algara's design, which treats each iris radio as a separate object, we used the UHD USRP multi-USRP object, which is treats all the multiple radios through a single object. So we implemented the base station UE worker classes to support the TXRX streaming between the servers and the USRP software-defined radios that serves as either base station or the UE. And these worker classes handle the task and provide an interface to the real-time DSP pipelines, as shown on the right-hand side. The real-time DSP pipeline includes multiple dual classes, and for each handles the signal processing task, such as the FFT, the channel estimation, the beamform equalization, the demodulation, and decoding, etc. So taking the uplink transmission as an example, each UE captures beacon signals sent out by the base stations, and it then transmits and synchronizes the timestamp with that from the base station. It then transmits a sequence of uplink and pilot data symbols following a predefined frame schedule in the JSON defined in the JSON format. The base station then extracts the uplink CSI using the receive uplink pilot and performs the demodulation and decoding of this uplink symbols. So overall, the DSP pipeline reports in real time the different matrices of measuring qualities of the transmissions, such as the signal to noise ratios, the EVM, BER, and BRER. In addition, we also provide the HDF recorders to post-analyze the results of the recorded IQ samples. So although most of the recent study has been focusing on the software-based baseband processing for large-scale sub 6 GHz MIMO systems, while 5G also embraces the millimeter wave frequencies band to achieve further improved data rates, leveraging the widely available spectrum. So taking this picture as an example, we can see that the 5G new radio millimeter wave usually uses the WiNTECH'23, which has this following parameters, which has the subcarrier spacing of 120 kHz, the sampling rate, which is much higher compared to the numerology 0 settings, and the FFT size and the RB sizes. And since of the new nature propagation characters of the millimeter waves, for 5G FR2, it already has less spatial streams, but higher bandwidths. So it's interesting to investigate how the performance looks like in the 5G FR2. So this leads to our second contribution, which is we integrated the 28 GHz phased array antenna modules, which is the POM board, to integrate with our Algara UHD. So with this design, we are able to not only test the 5G FR1 massive MIMOs, but also test the performance of 5G FR2 on millimeter waves with the POM boards. So this is shows an example of our system setup on the PAL Cosmos testbed. It's deployed in the Cosmos Sandbox 2 in the indoor environments. So the left-hand side picture shows the IBM 28 GHz POM boards. And in the middle shows the USRP devices that we used. On the right hand side, it shows the connections between the USRPs and our POM boards. So in order to run in the millimeter wave frequencies, we use the IBM 28 gigahertz 64 element POM boards, and the POM board has a IF interface at the 3 gigahertz, which are connected to the USRP's RF front end via SMP to SMA coax cables, and perform signal up or down link or up or down conversions between the 3 gigahertz and 28 gigahertz. And using a Python controlled APIs, the users is able to configure and control the POM board by sending API commands to the microZ FPGA plugged into the POM board via the Ethernet interface. Since each of the POM board is driven by its own onboard PLL, which is the phase lock loop, we actually apply once the cross CFO calibration during the initialization. So the following two pictures shows the histogram of the measured CFO between the two POM boards in two directions, which is the uplink and downlink. And we then calculate the mean values of the estimated CFO and then apply that to the onboard PLL. The resulting residual CFO of the is going to be around 1 kilohertz across the 28 gigahertz link, and which this can be further calibrated during the equalization of the received signals. So the next we're going to dive into the wireless quality of transmissions for the experimental evaluations. So we first present the SNR versus the EVM curves here. So for experimental settings, we choose the WiNTECH'23s, and which has the subcarrier spacing of 120 kilohertz, the sampling rate of 122.88 megahertz, and the FFT size of 1024, and the number of resource block is going to be 64. So we tested the SISO and MIMOs with the polarization MIMO with the 16 QAM and 64 QAM respectively. So where from the graph you can see that the MIMO performs a little worse than the SISO cases, which is caused by the interferences between the two polarizations. So in the 16 QAM, we can see that with the SNR larger than 25 dB, we have a EVM less than 12.5%, which in this case is 9.71%. For the 64 QAM cases with the SNR larger than 30 dB, we can see a EVM less than 8% in this case, which is 7.53%. We then present the SNR versus the BR curves here. It's following the same numerology 3 settings, but analyzed in the different modulations and coding schemes. So we presented the MIMO settings with the code rate of 1/3, and also MIMO settings with the code rate of 2/3. So from both of the plots, we see that under the same SNRs, the performance for the 16 QAM is better than 64 QAM, which is expected. And with a higher code rate, to achieve a similar BR performance, we need a higher SNR values, which is also expected. So for code rate of 1/3, we can see that the SNR with the SNR larger than 20 dB, for 16.4 QAM, we are able to achieve the BER of 10 to the less than 10 to the power -5. However, for 64 QAM for code rate of 2/3, we actually need a much higher SNR, and the BER performance is not as good as a lesser code rate. So then we present the baseband processing time, which is there's a two evaluation matrix we choose. The first is the CPU time, which is the actual time that during the task is being executed by the CPU. We take an example as a FFT, which is for the 14 OFDM symbols in one slot. The CPU time for FFT is only going to be the time that's going to be executed by the CPU to process the IQ samples to do FFT. And the elapsed time is the total time it takes to finish processing a slot, which in this case is from the beginning of receiving the first packet all the way to the end of finishing processing the decoding of the last OFDM symbols. Presented the 2x2 polarization MIMO with the 25%, 50%, 75% and 100% traffic load respectively for both CPU time and the elapsed time. So from the left-hand side, you can see that with the number of cores, worker cores increased, the CPU time actually decreases, which is expected since we have more worker cores to work on the same task. However, on the right-hand side, we can see that the things diverges when we increase from 8 cores to 16 cores. The elapsed time actually increases. And this is caused by the intercore communication overhead, which is even there we have more cores or less CPU times. The intercore communication is going to cause the extra time between the core communications and causing the elapsed time to increase instead. So from this, we can see that with 8 cores, the Algar UHD can meet the real-time requirements with the 50% of traffic load in this case. And we further break down the CPU times into 5 different categories, which is the FFT, CSI, beam weight, demodulation, and decoding. And we presented the results for the 75% traffic load and 100% traffic load for different scenarios, such as the SISO with 8 cores, MIMO with 8 cores, SISO with 16 cores, and MIMO with 16 cores. And from all those different scenarios, we realized that the decoding is actually a bottleneck. And this leads to our future work, which the first task we're going to do is to build a larger scale programmable MIMO radios in the millimeter wave frequency band. The second is the optimization of the baseband processing, targeting on the 5G NR FR2 physical layer traffic patterns. And the third is the integration of the dynamic beam tracking and the management schemes with the deployed programmable millimeter wave MIMO radios. So thanks again for listening, and we have also open sourced our code and tutorials online, and feel free to email me if you have any questions, and thanks for the attention.